Many times in programming, we're given a problem where there's an easier tool to use, but sometimes we just need to find it. And I remember when I first started programming in JavaScript, we I would have something like this where I needed to take a value and manipulate it in some way and then accumulate it. And I would always use a for loop. That was the only tool that I knew. When you only have a hammer, everything looks like a nail. And as I got more and more into JavaScript, I started learning about different kinds of things. And eventually, what I got into is I found for each. And I was like, oh, instead of running a for loop, I don't have to calculate the length. I can just say for each and then have it work that way. And that worked for a while. And a while after that, I think when I started getting to know it, I actually started reading the documentation. And much to my surprise, delight, chagrin, I realized that there was also a reduce function that worked with arrays. And my life was changed because finally I could do something that was actually built into the language that was a little bit more optimized. I didn't have to find the length, but I also could just return it and get the value instead of having another variable that was always being used outside the loop. And so, in that way, assembly is kind of that way, but again, we only have about 16 instructions in um, the core set of instructions. The multiply instructions were not part of the core instructions, and so the multiply instructions are kind of like a little bit of a gem that kind of appeared. And when they did this, they did do one thing that was very helpful, is that they introduced an instruction that you can multiply and accumulate. And so we can do this program very easily without adding like we did in the factorial example. So let's get started. So the first thing that we need to do is we need to load the array of numbers that we're going to actually work with. And we'll put that in register form because that's the first one that we'll use. And so after we have this main group of numbers, we can just go right into running our loop. We don't have to worry about anything else right now. We want to load the first number. And as you can see at the bottom, these are all bytes. So we have to do load register byte. And we'll put this in R5, the number that's at the address of R4, and we'll increment it so that we can get to the next number. And we'll come up here, and we'll put R5, we'll say red number. After that, we need to, first of all, see if we've hit the end, as we do with a lot of these loops, is make sure that we haven't hit the end. And so we'll compare this number to 0. And as you can see, I put a null byte at the end of the input data. And if we do, then we have to get out of it. We have to get out of this loop. And so, again, I'll just use an exit label because it makes sense. It's easy to look at and understand. If it's not, though, what we need to do is we need to multiply it and accumulate it. So first of all, we need to put somewhere, we need to find somewhere to accumulate these numbers. So let's do R6 will be the total. And this is essentially what we need to put is R6 equals R5 times R5 because we're squaring R5 and then adding what was in R6. And you can see here that we have the multiply and accumulate. We have the multiply, we're going to use R5 twice, and then we're going to add the R6. And so the command for this is MLA, multiply and accumulate, and the first operand is the destination. And the destination here is going to be R6, as we can see. The next two operands are the numbers we want to multiply, which are R5 and R5. And then the last operand is what we want to add. So what this allows you to do is at the end of this, where we have the plus R6, we could have a plus R something else and store it in R6. It doesn't have to be, the accumulated number doesn't have to be the register that we're storing it to. And that's all we need. We've done all that math in one operation. And now we just need to go back up to loop. And so if you, again, think through this, 65, it's not 0, so we won't break. We multiply 65 times 65 and add it to R6. And let's actually initialize that. Again, not something you need to do because you should get a 0 in the register when the program runs. But again, something that I like doing just so that I can see it. 65 times 65, add it to 0. So in the first one, we have 65 squared. We go back up to the loop, and then we load the next byte, which is 71. It's not 0. And then we do 71 times 71, and we add it to the 65 squared. And it'll just keep going on and on and on. So the next thing that we need to do is we need to do the integer to ASCII so that we can display it to standard out. If you remember the last one, I edited the integer to ASCII code so that it's easier to use in this kind of process. We have down here an outstring area that is 11 bytes is what we need for the integer to ASCII call. And so we just need to set that up. I2O, integer to ASCII. And if you remember, the first parameter in R0 is going to be the number that we want to display, which we stored in an R6. And then the next one is the address of our output. So we'll use load register into R1, and then we'll put outstring. And then we're going to branch and link to our ITOA. And you should be able to see now some of the benefits of being able to write these in external files. We've cut down on the number of lines in one file by a lot, and it makes the code a lot easier to read. The next thing we need to do is we need to actually write this out because our ITOA doesn't write. So our supervisor call number is 4. So in R7, we'll put number 4. Our first parameter is the file descriptor, and it's going to be standard out, so it's 1. The next thing we need to do is provide the address of the string we want to write. So we'll do load register R1. And this isn't necessarily a no-op. You can see a couple lines above, we do the same thing. But remember that because it's in the first couple of registers, there's no guarantee that it's going to be saved. If you look at the ITOA file, it also says that there's no guarantee that the first couple of parameters will be saved. Anything from R4 on will be, but not this. And then the last parameter in R2 is the length, and our max length is 11. Doesn't necessarily mean we're going to use 11 characters, but it could. And then we're going to invoke that using SVC and 0. And the last thing that we need to do is actually exit the program. the supervisor call for exit is 1. And then the only parameter that we need is an R0. We're going to put 0 for no error. And then invoke it with SVC and 0. And that is really all we need. And if you look at it, it's kind of interesting because we have 42 lines. I know they're not all code, but we have 42 lines here. Really, the whole program functions in one line. You look at line 24 here, and it does all the actual work, which is kind of interesting to me. So just to review, in the make file, I have both the main.o and the I2A .o file here, so it'll compile both files. And then you need to make sure that you have your I2A as integer to ASCII source file in here. If we run make, everything looks good so far. We run the program, and we get 78607. And if I look at what we should have gotten, that's correct. And so I guess my main point is never be afraid to look at the documents, even if you've been using a language for a long time, whether it's assembly or whatever language you use on a day-to-day basis. A lot of times, a lot of these common things are there, and you just need to know that they exist.